Hello and welcome to another lecture of classical motion of a single particle. We have already discussed different situations of a simple harmonic oscillator without any forcing and damping, with forcing without damping, with damping without forcing, and also with both forcing and damping. We have also discussed different type of solutions. We have discussed an interesting problem. We have discussed very briefly the interesting phenomenon of beats. And finally, now in this lecture we will start a very interesting topic, that is the motion of a particle, a single charged particle in an electromagnetic field. Now, you see, if you want to pursue domains like plasma physics, plasma astrophysics or laboratory plasma physics, you will need this very concept, okay? And many phenomena can be described in terms of this type of motions, okay? And that is why, so in this lecture I will just give you some introductory concept of this motion and some interesting aspects, a little bit more advanced topics will be covered in the next discussion. Okay. So, first we will be taking this condition that I have a particle of charge q which is moving or which is placed in an electric field, external electric field E. Okay. Now, of course, just before starting I would like to mention that why I am discussing this concept here, because it actually will use the basic concept of simple harmonic oscillations as well, as you will see. Okay. So, first I am just thinking that I have a uniform electric field E, and in that field, okay, a point charge of plus q, okay, is placed. Now, you know that if it is placed, then of course, the force which will be acting on this particle will be q E, okay. That is the law, okay, that E, if E is the electric field and the charge of the particle is q, then the electrostatic force or the electric force which is experienced by the particle will be q E. So, this will be actually the force which will try to cause acceleration in that particle. The particle will also have some mass which is m, and the particle will have some acceleration due to this force. So, that I will call it as m v dot or m r double dot. Okay. So, you see that you can actually then the equation becomes m d2 r dt2 is equal to q E. So, now you can actually write for every direction, you will simply have m d2 x dt2 is equal to q E x, and so for y and z. Okay. So, this is something very interesting. Now, let us say this one is a constant field, uniform field, okay. It does not change with time and space. Then this is a constant as well, because when a vector is constant, okay, its direction and all the components should be. So, whenever the vector is written in Cartesian coordinate systems, okay, every component should be also constant for a constant vector. Okay. Because every component is actually associated with a constant direction. Okay. So, that is why this is constant, and if this is constant, I know how to write the equation. So, that is m d2 x dt2 is equal to q E x, and then dx dt will simply be equal to q by m E x times t, okay, plus some constant of integration C1, and then finally you write x which will be equal to q by 2m E x t square plus C1 t plus C2. Okay. So, you see once again, so this will be the displacement in a single direction, for example, x direction will be a parabolic function of time. This type of problem we have discussed much earlier. okay, and it will be a case of actually uniform acceleration, okay, given the particle is not changing its mass by any complicated process. Okay. Now, if we are now considering the motion under a constant field B, okay, then what happens? So, first of all, from the law of electrodynamics, okay, we know, or actually from the Lorentz force law, we know that if a particle Q is placed in a magnetic field B, which is also uniform, okay, for the sake of simplicity we assume that is B is uniform in time and space, then in general there is no motion due to this B. But if you, so in general, if the particle is just at rest, then no force is caused by B on this charge. But if the charge is already moving with some velocity v, or I mean let us say, I am causing some velocity, okay, I am just preparing my the system with some initial velocity v, then that velocity can cause a magnetic force which is called a Lorentz force, and that is given by Q times V cross B. Okay. So, this is the force on a charged particle due to a uniform magnetic field when the charged particle is moving with a velocity v. If v is 0, this force vanishes. Okay. Now, here I am just considering that there is no electric field, only magnetic field. Okay. Somehow I have made this velocity. Okay. Once I have made this velocity initial, then it will experience this force and it will try to accelerate. Okay. So, I am just trying to write this Newton's law for this. So, it will be m, then dv dt. So, equation of dynamics, that will be given by m dv dt is equal to q v cross b. Okay. Now, since I have this form, already I have said that this form will not change the kinetic energy of the particle. Okay. And that means that if you do m v dot dv dt, it is 0 because this is v cross b. So, v cross b dot v is 0, and that is why ddt of half mv square is 0, and that is why you can say that this type of force cannot change the kinetic energy. And from your concept of work energy theorem, you know that if kinetic energy is not changing, then there is no work done by or on the system, and that means that this type of force is actually not doing any work or also not helping the system to do any work. Okay. So, this type of force, that is why is known as no work force. Okay. However, it causes acceleration. Okay. And now we will see that what will be the trajectory under such force. See, if I have such a force, I can actually say that since my B is uniform without losing generality, I can choose. So, if B is a uniform field, it should have a constant direction. I can choose that constant direction to be the z direction, and B I can write is equal to simply B z cap, okay, or equivalently B k cap, because I sometimes use these two, okay, both z cap and k cap. If I write this, then what will be my V cross B? So, V cross B will simply be, I can write Q times V cross B. So, Q I j k V x V y V z 0 0 B, and you will see that with I cap you will have BVy with j cap you will have minus BVx, and with k cap you will have nothing. Okay. So you will have actually QBVy I cap plus QBVx j cap. Here I should write a minus, there is a minus sign. Okay. And so I can now write for 3 components MVx dot will be equal to simply, so that is the x component and that is mvx dot. So from Newton's law, so this is Newton's second law, mvx dot is equal to qbvy, mvy dot will be equal to minus qbvx, and what will be mvz dot? Interestingly, that will be 0. So there is no acceleration in the direction of the magnetic field, okay, in the direction of the uniform magnetic field. So in the direction of the uniform magnetic field, Vz is constant. Since this is a parallel direction to the B field, I can call that V parallel, okay, and this is a constant for my motion. Okay. So what to do with these things? You see, these two equations are coupled. So you may think that how to solve them. So Vx dot is exactly equal to Vy, and Vy dot is exactly equal to minus Vx with some other constants, of course. But how to solve them? Then your knowledge of simple harmonic oscillator would be superb helpful, and you can say that okay, I take the another time derivative of this equation, which will be m Vx double dot, which will be equal to QB Vy dot. Now what is Vy dot from this equation? This is, so QB Vy dot is nothing but minus QB by m Vx. Okay. And if you have this type of situation, then you can easily say, okay, I have Vx double dot is equal to minus q square b square by m square Vx, and I have Vx double dot plus omega g square Vx is equal to 0, where omega g is equal to QB by m. Okay. So omega g here is QB by m, and you have now what? You have the equation of a simple harmonic oscillation, but now this simple harmonic oscillatory solution will be for Vx. So this actually says Vx will be equal to some simple harmonic oscillation. So I can actually write some equation, let us say some V0, okay, some V0 cos omega t, omega gt, okay, omega gt plus alpha. Let me also for simplicity choose, for simplicity let us choose alpha is equal to 0, then Vx will be simply equal to V0 cos omega gt. Okay. And if you have this, then of course what will be Vx dot? Vx dot will be minus V0 omega g cos sin omega gt, and this is again from our previous equations. Vx dot is nothing but QB by m Vy. So, this is QB by M Vy, so that is omega g Vy, okay, and comparing, so comparing we get Vy is equal to simply minus Vy will be equal to minus V0 sin omega gt. Okay. I also have Vx is equal to simply V0 cos omega gt. So, from this two we have V0 square is equal to Vx square plus Vy square, and this is a constant. Now, this is what? This is the modulus square of the velocity in the plane perpendicular to B, right? This is in the xy plane. This is the modulus of the velocity in the xy plane. So, I can write that as V perpendicular square, okay, where I can write that if I can write that V square is equal to V parallel square plus V perpendicular square. So, this is given by Vz square, this is given by Vx square plus Vy square, okay. So, where? Yeah, okay. If I write this, then I can again write, so Vx V perpendicular cos omega gt Vy is equal to minus V perpendicular sin omega gt, okay. Yeah, I think this is completely okay. If you now do the same thing with Vy, you actually also can show that Vy double dot is also equal to minus omega g square Vy as well, okay. Now, if you are given with these two relations, then you can easily integrate and you can find the solution for x and y as well. So, here what will be the solution for x? So, x's solution will be, so x will be simply equal to V perpendicular by omega g. So, that will be actually dx dt is equal to this. So, cos sine, yeah, so that will be sine omega g t, yeah, and Vy will be, so with plus of course x0 which is the constant of integration, then Vy you will have y is equal to V perpendicular by omega g, and then you have minus cos omega g, but there is a minus, so finally it will go away and you will have cos omega g t, okay, plus y0, okay. Then finally again you will have x minus x0 is equal to V perpendicular omega g sin omega g t, and y minus y0 is equal to V perpendicular by omega g cos omega gt. What is the message from that? That is, if you now do the squaring adding of these two, you again will have x minus x0 square plus y minus y0 square will be equal to V perpendicular square by omega g square. I call that some radius rg square, and I call this omega g as the gyration frequency. Of course, omega is an angular frequency, so it is angular gyration frequency or gyration angular frequency for gyration, and Rg is called the radius of gyration. Okay. So, or we can call here the gyro radius. Okay. So, if the particle is ion, then it will be the gyroradius and the gyrofrequency, gyration frequency, sometimes we will also call gyrofrequency. Yeah. So, that will be, if the particle is ion, then they will be corresponding to the ions. Okay. So, that means the gyrofrequency and gyroradius of the ions. If they are electrons, they will be gyrofrequency and gyroradius of the electrons. So, since they are positive quantities, okay, so in general in their definition, so for example, when I say omega g, the proper definition is actually q b by m with a mod sign. So, that if even if q is negative, your frequency is not negative. Okay, that is our convention, and same for the gyroradius. So, gyroradius actually you can simply write. So, what is this? This is, so v perpendicular by omega g. So, omega g is q b by m. Okay. So, here again you will have a mod sign, so that even q is negative, you will never have these to be negative. Okay. So, you see that in the xy plane, finally the particle is moving in a circle of radius rg and with its center as x0 and y0. So, these x0 and y0 are called the guiding centers, guiding center. Okay. Now, what I am trying to say here, that you see that in this xy plane, if you just see the particle, so if this is x direction and y direction, the particle is moving in a circle like this, okay, and this is your rg. But we do not have to forget that the particle is also having a constant velocity in the z direction. And now, if we just say that we are just seeing the motion of the particle in such a way that z direction is this and your x direction is this and y direction is this, okay, then of course, in this plane it will always make a circle. But now, in this direction the particle is also having a constant velocity. Then what is the resultant trajectory? The resultant trajectory is neither a straight line nor a circle, it will be a helical structure. Okay. And this type of structure we actually called a helix. Helix. Okay. And the helix angle is an angle, okay, and the helix angle is defined by tan inverse. So, we can call this as alpha, tan inverse v perpendicular by v parallel. So, in a sense this is actually a measure of the ratio of this perpendicular displacement to the parallel displacement in unit time. Okay. So, this is what is all about this trajectory under a constant magnetic field. Okay. The situation can be, of course, be a little bit more sophisticated if you add both E and B field, if even if they are uniform, and then you can further refine the motion if you just say that they are no longer, the fields are no longer constants. Okay. And this type of motions can be of high importance in the case of plasma. One last thing is that in such type of motion, whenever for example, you are just thinking the motion in the plane perpendicular to the uniform magnetic field, it is actually a circular type of motion, and the motion of the particles are in such a direction that finally the motion is actually gives rise to a, so whenever you have a particle, a charged particle which is moving like this, this motion actually gives rise to a current which is nothing but the charge times the frequency of the rotation. Okay. Here frequency means the true frequency. So, the current due to a rotating charge is nothing but the charge times the frequency of rotation. Okay. So, this current will be in such a direction that the resulting magnetic field will be opposing the initial magnetic field to which the particle was subject to. Okay. And that is a beautiful phenomena called the diamagnetism or the diamagnetic effect, okay, and this is nothing but to make the whole system consistent with the conservation of energy. Thank you very much.